Hey guys, welcome back to day 22. Do some Lewis structures today. So let's dive right on in. H2. So hydrogen gas. First thing we have to do is count the valence electrons. Each hydrogen has one electron, and since there's two hydrogens, there's two valence electrons. 2 electrons total. So we're going to put the two H's usually on the same line of the paper. Can they be vertical like this? Of course. Can they be at a 45? Yeah, it does not matter the angle. Each hydrogen has an electron. And what happens is that these two electrons pair up to make a 2-electron bond. So as you can see, this is a 2-electron bond. So we'll actually draw it a lot of times as just a line to represent the 2-electron bond. And that's what we get. And so if we do it vertically, it just look like that. So there's H2. Probably one of the easiest Lewis structures to draw. Let's go with HF, hydrogen fluoride. Electron count. We have 1 for hydrogen and 7 for fluorine, so that's 8 electrons. HF. The first thing we do is have to bond them, and that's 2 electrons. So we're bonded, now we have 2 electrons. Hydrogen is full with its duet, so let's go to then 4, 6, 8. So I filled in the octet of the terminal atom. We have no central atoms yet, they're all terminal at the end. So there is 8 electrons for fluorine and 2 electrons for hydrogen. So if we look at this, I have 2, 4, 6, 8 there. And we have 2 there. So we are sharing the appropriate amount of electrons for each atom. Happy. Let's try F2. Electron count, 2 fluorines, and then each fluorine has 7 electrons. So now we have 14 electrons. 2 F's. So I'll have a blue F and a green F. We're going to bond them. 2. Then fill in the octets. 4, 6, 8, 10, 12, 14. There we go. The blue fluorine has 2, 4, 6, 8. And the green fluorine has 2, 4, 6, 8. Shared electrons, which is the bond. Then we have lone pair, which is non-bonding. Continuing. Try oxygen. O2. We'll do O2, and then we'll do N2. So oxygen, how many electrons valence does oxygen have? Well, oxygen has 6 electrons, and there are 2 of them. So we end up with 12 electrons. 2 atoms, so they're just going to be next to each other. O, O, bond, 2, 4, 6, 8, 10, 12. There we go. Doesn't look good to me. Why not? Well, 2, 4, 6. That's not okay. That 2, 4, 6, 8 is good. So what do? Do we remove one of those electrons and put it here to make it even, make it fair? Well, fair is just a viewpoint, and that's not fair. Fair doesn't work because now they both have 7. 7 does not equal 8. So when we don't have enough electrons, there's too few electrons, we form a double bond. So it doesn't matter if you take this top pair, the pair on the side, the pair on the bottom. It does not matter which one we take. I'll take the top one, draw a double bond. So what happens now? Now the oxygen on the left has 2, 4, 6, 8. We're good. The oxygen on the right has 2, 4, 6, 8. We're good. So we made a double bond when there's not enough electrons. Nitrogen. 2 nitrogen each has 5 valence electrons. 7 electrons total, but 5 valence. So that gives us 14 electrons. 2 nitrogens, N and N, bond 2, 4, 6, 8, 10. Well, do we do it this way? How about that? Nope, that's still not good, right? We have 2, 4, 6, 2, 4, 6. Doesn't work. So we form multiple bonds as possible. So there's one double bond, and another triple bond. So this is a triple bond. Nitrogen on the left, 2, 4, 6, 8. Nitrogen on the right, 2, 4, 6, 8. So it works out. So nitrogen, N2, nitrogen gas, is a triple bond. Moving on. Now let's talk about central atoms. They have more than one atom bonded. They are typically written first in the chemical formula. They are not H and or F. So H is not a central atom. F is not a central atom. It's typically written first, and usually the least electronegative. Now, we haven't defined that in lecture yet. If you've read the textbook, you probably know what that means. It's the least likely to pull electrons to itself. But it's usually written first and the least electronegative. So let's do some examples. We'll do CH4, and we'll do NH3. So methane and ammonia. Electron count for methane, 4 for carbon, plus 4 times 1 for hydrogen. That gives us a total of 8 electrons. So who's in the center? Well, it's not hydrogen, and carbon's written first, so carbon will be in the center. So right now, I'm just going to north, south, east, west, up, down, left, right, the hydrogens. That's not how it actually looks. Some of you guys already know it's a tetrahedral molecule, and they're not 90 degrees apart, the bond angles. But for our Lewis structure wise, this will be great. First thing we do is bond everything. 2, 4, 6, 8. Is there anything I can do? Well, each hydrogen has 2 electrons being shared. Happy. Carbon has 2, 4, 6, 8 around it. It's happy. That's it. That's methane. 4 CH bonds. Let's look at ammonia. 5 electrons for nitrogen plus 3 times 1 electron for hydrogen gives us 8 electrons as well. So we got nitrogen, 1, 2, 3 hydrogens. Bond. 2, 4, 6. I have 2 extra electrons. Well, where do they go? Well, if we go back to our guidelines, extra electrons go on the central atom as a lone pair. So now we have lone pair of electrons, which is non-bonding. They're still there, they still take up space, they still exist, they're just not bonding. So now nitrogen has the 2, 4, 6, 8, and each hydrogen has 2. And we're happy. Water, let's do water. H2O. So water has 2 times 1 electron for hydrogen, plus 6 electrons. So that's total 8 electrons of valence total. How is this arranged? Well, oxygen is going to be in the middle because hydrogen cannot be in the middle. All right, hydrogen cannot be in the middle. It will not be in the middle. So let's bond. 2, 4. Extra electrons go on central atom. 6, 8. And there is water. Oxygen has 8, and hydrogen each has its 2. Let's talk about CO2. Electron count. 4 for carbon, plus 2 times 6 for oxygen. So that's 16 electrons. Who's in the middle? Probably C. So O, C, O. Bond. 2, 4 octets. Terminal atoms 6, 8, 10, 12, 14, 16. Perfect. Each oxygen has 2, 4, 6, 8. 2, 4, 6, 8, and carbon has 2, 4. Ooh, that's a problem, isn't it? Carbon does not have enough. What shall we do? Well, if we have too few on the central atom, we form double bonds as necessary. So we're going to double bond from each oxygen. Could you technically triple bond one side and single bond the other? It's not it's a valid Lewis structure. I wouldn't mark it wrong, but there's a reason there's a double bond on each side, and we'll get to that reason. First, let's talk about exceptions to the octet rule. Let's talk about some exceptions to the octet rule. Okay. First exception is that obviously hydrogen and hydrogen only needs 2 electrons to be like helium. And we've already been doing that. 2. All right. Some elements can have too few electrons. And these are the elements before carbon. That would be obviously H, He. I'm going to change the color there. He, because He is not going to bond for us. We're going to have Li, which we won't really bond. Be and B. They can all have less than 8. Obviously, 2, 2, 2, 2. And this usually can have up to 6 electrons. It can have 8 electrons as well. So you can have, it'll do 6, it'll do 8. 3, too many electrons. Elements in the third period and below can have more than 8 valence electrons. Well, who would that be? That would be such as, technically Si is in that period. We don't ever do anything with Si. So we got Si, we got phosphorus will, sulfur will, chlorine. Right? Argon is in that period, but argon doesn't bond. We're not going to make any compounds with argon. Right? Arsenic will, selenium could. We have bromine, krypton. Krypton will have a couple compounds that we could draw. We'd have antimony, tellurium, iodine, and xenon. And those will be the ones that would actually violate the octet rule in our class. And lastly, we can have an odd number of electrons. And these are called radicals, such as NO2, small. Right? They are very reactive. They're not covered all that much because they're, about 10% or less of all the reactions that, we observe. But they are very reactive. And they're actually very important for, I guess, biological processes. Again, I'm not a biology person, but a lot of biological processes, there's some radicals in the body. Like that's why we have to eat antioxidants. And so, for example, this radical here, NO2, we have 5 plus 2 times 6 electrons. So that gives us, 17 electrons. And so if we look at this, ends in the middle, it's written first. O, N, O, 2, 4, 6, 8, 10, 12, 14, 16, 17. Or if I double bond one of the oxygens, doesn't matter which one, that's my Lewis structure. And so if you can see, the lone electron here is not stable, so it's very reactive. So those are some exceptions to the octet rule.